We're starting now into kinematic equations, and I want to point out first and foremost, you'll see I've written in pink at the top there, that these equations are only useful for uniform acceleration. So if you have motion that would form a VT graph that would have more than one line, then you cannot use this for the whole thing. It can only be used if the acceleration is constant. So one acceleration for the whole motion. We'll start with a couple that we've already come across because we've seen them from our graph work. You'll see here I started that from VT graphs, we've figured out that acceleration is the change in velocity over the change in time, which means acceleration is v2 minus v1 over the change in time. And I will often just write change in time as time. I won't put the change in. So if you see it written as just t, it means the same thing. And I'm just going to rearrange this a little because there's a form that we see it in more frequently. We often see it as v2 equals. So I'm going to move my delta t here by multiplying both sides by delta t. So I get acceleration times delta t equals v2 minus v1. And then v2 equals v1 plus a delta t. So that's the one I see it as most frequently. And if you look there, we would often have displacement as one of our variables, and we don't see it here. So in this equation, this is the one variable that's missing. And this is how I've set up this chart over here to record all of our equations. Because there are 5 variables that we deal with: d, t, a, v1, and v2. So there's 5 equations, there's 5 variables, and we can actually come up with 5 equations that relate them, and each one is missing one of those variables. So the one that's missing, delta d, is the one we just finished there. v2 equals v1 plus a delta t. And then also from our VT graphs, we learned how to look at average velocity, and you would have seen before that average velocity is delta d over delta t. So this one here, I've just rearranged it. Okay, so we have delta d equals v average times delta t. And we also know that on a VT graph, that average velocity is equal to v1 plus v2 over t, or 1/2 times v1 plus v2. Right, so that's what I've got here. Right here. This is equivalent to average velocity. I've just substituted in the expression there. So now we've got another equation. You can see this one's missing acceleration. It has the other 4, and this can be written in different forms just like the other one can, but this is the one you'll see it written in most often. So we'll put that one up here. So this one's missing acceleration, and I'm just going to rewrite the equation beside it. Delta d equals 1/2 times v1 plus v2 times delta t. And now we can use these 2 equations to derive the other 3. And on the next slide, we're going to do that with one of them. Before I move on with this example, I just want to point out that your textbook uses VI and VF, and it's exactly the same thing. The I and F in the textbook stand for initial and final, and here I'm just using 1 and 2 for, as in the earlier situation 1 and then situation 2, so where it starts and ends. I don't like to use the I and the F just because it doesn't have to be a start and end. Maybe you're asking a question about something that happens in the middle, and the subscripts don't really mean anything. As long as you know which one is the initial and which one is the final, that's all that matters. You can use I and F or 1 and 2, that's totally up to you. So we're going to derive a third equation here. I've rewritten the 2 that we already know. And we're going to start by substituting equation 2 into equation 1. And if you recall from math, that means we're substituting in for this. So this is going to go into here. So we're in effect going to get rid of v2. So the equation we're creating is going to be missing v2. Okay, so we're going to sub 2 into 1. So we're going to get delta d equals 1/2 times v1 plus v1 plus a delta t, right? Because we have put in this whole segment here in for v2. So that whole thing has to be in the brackets there, and then all of that is multiplied by delta t. We can simplify this a little bit. We'll get 1/2, and v1 plus v1 is 2v1 plus a delta t. And now we're going to have to multiply in the 1/2 and the delta t that are on the outsides. So 1/2 times 2 is 1. So we've got v1 times delta t. So this first step here is we're multiplying this and this and this, and it's going to give us v1 delta t. And then we just finish our distribution, and now we're doing the 1/2, the a delta t, and the delta t. And that gives us 1/2 a delta t squared. So there's my new equation right there. I get delta d equals v1 delta t plus 1/2 a delta t squared. So there's my equation 3. So if I went back to the first page of my lesson here, remember the missing variable we were listing, so you can add this to that part of your note, and then the actual equation was on the right side. So this time the missing variable is v2 as predicted, and our equation delta d equals v1 delta t plus 1/2 a delta t squared. And you can go through a similar process and create the equations for the other two as well. And it gives us two equations, one that's missing delta t, and that equation will be v2 squared equals v1 squared plus 2a d, or delta d, that's what you're used to seeing, and also one that's missing v1. And v1, that equation, it's going to look a lot like the one that's missing v2, and it's going to be delta d equals v2 delta t minus 1/2 a delta t squared. You can see the differences. We've got v2 in here instead of v1, and it's minus instead of plus. So now you've got your 5 equations, and you'll be able to go ahead and use them. I'm going to do a quick example for you on the next slide, and then you're going to be trying some questions, and I will post a second video with some more examples with some more complex ones, but for now you're going to work on solving using the grasp method and making sure you're using the correct equation and rearranging it as necessary. Alright, so here we go with an example. In this example, a car starts from rest and accelerates uniformly over a time of 5.21 seconds for a distance of 110 meters. Determine the acceleration of the car. Okay, so I've kind of done the basic setup for this question here, showing you the parts that we're going to do. I always draw a diagram. Almost every question in physics, this is what I'm going to do, because it helps me to visualize the question, make sure I have everything straight. So I've shown you I've got a little car there. It's a terrible drawing. It's probably the best you're going to get out of me. And I'm showing it's driving in a certain direction. It's going to go 110 meters. And I've even to find the positive direction. Because although that's not a huge issue in this particular question, it can be in some questions. So it's important to start now, get in a good habit, always to find a positive direction. So I'm going to start out here just by listing my given and requires. What do I know from the question? What am I looking for? First thing here tells us that the car starts from rest. So that immediately gives us a piece of information. It tells us that V1 is 0 meters per second. It is not moving at the start. It accelerates uniformly over a time of 5.21 seconds. So there's another piece of information. So time is 5.21 seconds. And there's a distance of 110 meters. So another piece of information here. 110 meters. And you'll notice that really, in fact, the directional part of it doesn't actually matter. So we can even drop the vector symbols. We don't really need them. The equation is going to work regardless because we're still dealing with 1D motion. We're still dealing with uniform acceleration. And now we want to determine the acceleration. So the acceleration is our unknown. So I put a question mark beside that one. And we can see that V2 is not used anywhere in this question. So V2 is the one not there. So we need to look for the equation that does not have V2 in it. So you can check out your trusty equations that you've written from the previous slides. And you should notice that we're going to use this equation here. Okay, so right now the equation is set equal to the distance, and we are looking for the acceleration. So we're going to have to do a little bit of rearranging here. We're trying to isolate for acceleration. So I want to start out by moving this v1 times delta t to the other side, because that's not so helpful at the moment. So I'm going to have this acceleration times time squared over 2 equals distance minus v1 times time. And I'll continue with my rearranging here. I need to move my 2, so I'll do that next. And it's divided, so I'm going to multiply to do the opposite. So 8t squared equals 2 times d minus v1 times t. And then I just have to get rid of my t squared. So that I'm going to need to divide for, because right now it's multiplied. And I'm going to run out of space, so I'm going to just pop myself up here. So I'm going to end up with a equals 2 times d minus v1t all over t squared. So there's my equation rearranged for acceleration, which is what I want. And now I can do the s part of my grasp, and I can plug in my numbers. So I've got 2 times 110 meters minus 0 times time. I'm not even going to put in the time because we know that that just ends up being 0. All over 5.21 seconds squared. Okay, and we can check out our units here. Take a look. We've got meters on the top, and because of this squared, we're going to end up with seconds squared. So this is going to give us meters per second squared, which is perfect because I'm looking for an acceleration. So this clarifies to me that my rearranging probably makes sense because I got units that make sense. So now I just have to finish up my math here. So we've got 2 times 110, so that's 220 on the top here. And the squared on the bottom, I end up with 27.4 8.1441. You should try this in your calculator at the same time just to verify you're getting the same answers. And then if we do 220 divided by 27.1441, I get 8.10489, etc., etc., etc. So I'm going to account for maybe 3 significant figures here. That seems pretty realistic given what we know. So our kind of raw answer there is 8.10489. So if I round that to 3 spots, then I get 8.10, and we know that this was meters, this was seconds squared, so this is meters per second squared. And now I just have to finish off by actually answering the question. So therefore, the car accelerates at 8.10 meters per second squared. And there you have it.